Okay, I was muted. James, just a moment to set up the speakers here in the conference room in Porto, because as you know, there are about 20 people here, and also others from Zoom, via Zoom, and also we have it live in YouTube. Sorry. Rita, can you see the screen? So, James,
lovely echo.
You're there. So, I'm very happy to welcome Professor James Covington in our virtual meeting here. We are in Porto, he's in the UK. And thank you very much, James, for participating in this meeting and for presenting today. Professor James Covington is professor in electronic engineering in the University of Warwick. He has many years experience and research in chemical and biological sensors, including enosis and detans. He has established the Biomedical Sensors Lab of the University of Warwick and has participated and coordinated a lot of European funded and national and also industrial projects in this field. So we are very happy to listen to Professor James Covington, because he introduces us to sensors and to artificial olfaction, which is a key activity that we have to develop within our WaterTOP network. So James, thank you, and the floor is yours.
Okay, can you hear me okay? So good afternoon, everybody. Welcome from a particularly cold and miserable UK. Winter has arrived here and it's horrible. So first I'd like to say, well, I was going to say thank you to Rita. So when Rita contacted me asking me to give this talk today, I kind of went, well, I'm not really into water. This is not my deal. But she was unfortunate enough to listen to me give a talk about olfaction at Eurosensors as part of their kind of one-day event, and asked me to do something similar here for you lot today. So I have done my best, and you shall have to kind of cope with it. So I hope that at least you'll learn something through today's talk. Oh, I like the way my computer just had it. Okay, so I thought I'd kind of give a thing about what I do. So I'm not a chemist. I don't work in analytical chemistry. I'm an electronics engineer, which makes me probably my presence here a bit weird, but can I get used to it? So basically what we do as a group is a lot of our stuff is things like materials. So firstly, everything we work on is in the gas phase. So we develop materials for making gas sensors. I'm an electronics engineer, so we do a lot of work in developing electronic devices for gas sensors and for odour detection. A lot of our work is developing systems, so we do a lot of work in industry. So a lot of the devices in the olfactory electronic noses have been developed in collaboration with our group and a number of VOC analysis systems. We've also done a lot of design work. And also we do a lot of work in applications. So companies come to us with specific requirements and we help them solve that problem. So this, if you don't know, is the Sony Aibo dog, which this is an early model. It's a photograph I had that I was working on. And we were helping Sony basically allow it to smell its owners. So Sony wanted to be able to fit gas sensors to their Aibo dog and then to recognize their owners and then go over and bark at them. And then we're trying to do this with chemical sensors, and that's something we worked on in the past. So I thought I'd kind of start by kind of mentioning things about the biological nose. So the biological nose is something we as electronics engineers try and inspire to kind of achieve. But it's really quite difficult. And if you actually think about how sophisticated the biological system is, it's it's incredible. So I saw that there's lots of talks about kind of techniques like GCMS, and I have my own GCMS system. And you look down this list and you think, well, a GCMS is pretty much as far away from this as you can get. So, it's non-invasive, it's real time. I mean, could you imagine trying to get GCMS to give you an immediate result? You don't, your biological system deals with all the sample handling. We carry it around with us all the time, so we can use it away from a lab. Our brain does a pretty damn good job of processing our data and giving us a result. But the kind of key bits at the bottom was, we don't require any vacuum. We don't require any pressures. We don't require any specialized gas lines. And although you could say it is battery powered in some way, we don't need to connect it to the mains, etc. So as an electronics person, this is something that we are trying to aspire to. We would like to try and create something as sophisticated as this. And I thought I'll stick a slide on about history. So this is a guy called Dr. George Dodd, who sadly passed away last year at the ripe old age of 81. And he was working, this is him on a TV show in the UK. And he was working on this idea of using replicating the function of human noses, or create these kind of things called artificial olfaction. So we were trying to do, or he was trying to do this as an alternative to the GCMS techniques, etc. And he created, or was part of the first company that was formed in the 1990s, which was the most successful electronic nose company ever, which is Alphamos. And people like him, and then people like me, have basically been working on this since the kind of 1990s onwards. So I joined the university kind of around 2000 and been working on this ever since. And this is the last photograph I have of George before he passed away. And as you can see, so he moved to the top of Scotland and became a perfumer. So he still lived in the world of olfaction even after the end of his academic time. So basically, how did we kind of set up this thing? So here is our attempt to create kind of some form of electronic nose sniffer. And this is kind of our comparison to what we do as electronics engineers to what our biological system is. So we have at the top here, does the pointer work, by the way, as I wiggle it around the screen? Is there a nod? I'll take a nod. Okay, so you have the human nose, which is kind of like to our electronic nose. We have olfactory receptors in our human nose, which are basically brain cells with little dangly bits on the end. And in our electronic nose, we have an array of sensors. So these are normally kind of gas sensors, which are commercially available. We then have, in the biological system, our olfactory display, whilst we as electronics engineers have data acquisition. And then we have some form of pattern recognition technique, which allows us to learn these smells. So if we go right. So in the case I went and found a photograph of somebody looking at some dodgy water, because that's the best I could do. So imagine that you are trying to analyze the odor from this kind of dodgy water thing. So we would take a sample, usually the headspace, so it's basically the air above the liquid sample. We'd pull it into our machine. The gas sensors within the machine would respond. So you can, this is a very typical response you see. So you see a sample in, you see a sensor response, and then you flush it out and get a recovery. Then you would extract some type of feature from this. So usually it's the kind of things like the differential, or it might be the speed of response, or some other features about this response. And then we would learn this using kind of some data processing technique. So we'd have an array of sensors. Each of these sensors would respond differently to the odors that are in the headspace. And then we could use pattern recognition techniques to learn these sensor responses. So you could train it, for example, just to have a binary yes/no test. So is this water good or is it not? Or I can use dual tests, or which one is the real thing, and etc. So it's very good at kind of classification in terms of two things and quantifying those two things, or telling you there's a difference. Quantification is a little bit more tricky with electron noses, but that's for another day. But the key thing of these is that you have an array of gas sensors, and that this array is comprised of sensors with a different property. So they'll either detect a different family groups. So you might have one for hydrocarbons, you might have one for toluene, xylene, that type of thing. And you might have ones for ketones or aldehydes or whatever. And I've kind of just put this slide together because the electronic nose term is a real umbrella term. It's not like, when you talk about mass spec, it's pretty much, you can fiddle around with it a little bit, but it's pretty much the same thing. With electronic noses, it's just an umbrella approach. So you're just having something which detects odor headspace and undertakes some form of pattern recognition. So the type of sensors that you can have in these systems are, almost infinite. And if you go around and look at electronic nose papers, you'll see hundreds of different techniques to measure these. So most of them, I've kind of broken this out into chemical or physical. So chemical, I consider as a way which the odor interacts with a chemical surface. So, for example, top one here is metal oxides, which is the most common one. You've got an odor which interacts with the surface. It's removing oxygen ions off the top of the metal oxide surface, and you basically measure the change in resistance. So these are where you have this physical interaction. And the top three, which are metal oxides, electrochemical, and conducting polymers, are the most common type of materials used in electronic nose sensors. There is a whole pile of other ones. I just put some examples in here for the purpose of today. So, I mean, nanomaterials, graphene and CNTs are very popular materials at the moment. So there's lots of kind of research in these areas, and people have constructed electronic noses out of them, but they are not commercially available. Hence the reason why the top 3 are highlighted. On the opposite side, you could do kind of physical measurement. In that way, you're measuring some kind of physical property of the molecule. The obvious ones are things like optical techniques. So you're basically putting light through a series of molecules and then measuring the absorbance. So kind of spectroscopy techniques. Photoionization, another common techniques, and ion mobility I should have put in there as well. So there's loads of kind of chemical and physical ways of creating these electronic noses, and it's a pretty common thing. So this is just photographing something like an emission stack, and these are some kind of common technologies then. So at the bottom here is our traditional electronic nose formed of a sensor array. These are kind of things that I use in my lab. These are this is a drift tube ion mobility spectrometer. So you just ionize the molecule, and then you basically measure the length of time it goes along a drift tube. So you just basically pull these along the electric field and push against a buffer gas and measure the time, and you get some differentiation. These are air-based mass spectrometers. So I've got a couple of these. So these are air-based ones, so you can just take them out in a field and they run off a car battery, and you can do mass spec on the fly. And then optical absorbance. So you can basically measure the amount of light absorbed by different gas molecules. So all of these different techniques are kind of under the electronic nose umbrella. Each of these has a good and bad, positive and negative technique. Electronic nose is usually the cheapest. Optical is very good for certain low weight molecular gases. Ion mobility is better for larger VOCs, and so on. So it's really kind of picking your technology that you like for your application. And, as a kind of research, I quite like this slide. This is a few years old, to give me some level of sensitivity. So here we are, down the bottom here is our dog, which is kind of our research target. And these are kind of various different technologies. This is a little old, so it could be that these have moved around a bit. And there's some optical dye stuff, which is further down here as well. But basically, this is kind of how we see it. So basic electronic nose isn't the most sensitive thing in the world. And this has probably moved down over time. But our other technologies, mass spec, ion mobility, SP is solid phase microextraction. So these techniques are getting on par with a dog. I mean, the dog does cheat a little bit. So if you watch a dog sniff, he doesn't sniff the air, he sniffs the ground. So he does use the ground as a pre-concentrator. And if you actually see, he blows air out through his nose and then sucks it back in again. So there is a question of whether or not this is totally true that he is down here, but I'm not going to get into that kind of conversation. I thought I'd put this slide together to give you some examples of kind of how these machines look like and how they would compare to a, kind of some of the challenges in electronic noses. So here is our mouse, and he has 1,430 different sensors, and he has one of these, many, many millions of each types of sensors. So it's a very high diverse array. He has many temperature types, and he can detect to the parts per billion, parts per trillion limit. Fantastic animal. And then here are 3 kind of examples. So this is a polymer-based machine. So this is a little handheld unit that we did the development work a couple of decades ago. So you can still buy these. They're about $10,000. And this has an array of 32 conducting polymer sensors, but it has no redundancy. You've only got the 32, which are all different. And these are PPM level machines. This is a metal oxide one. This is an AirSense analytical Pen 3, so I have one of these as well. They're quite small. They're only kind of big, but they're not battery powered. This is even less. So it only has 10 sensors. Again, no diversity, limited redundancy, but because they're metal oxides, you get a little bit more out of the sensors. So you might get parts per million, parts per trillion. This is a ion mobility spectrometer. So this is a GCIMS system. So I've got one of these as well. In where you only have one detector, which is just a metal plate. But by using it in a kind of temporal way, you can get quite a lot of information from it. But again, no redundancy, but we do have good diversity because of GCCOM, and it is at parts per trillion. So you can see, but this is kind of, $40,000. This is $20,000. This is $10,000. So you get, well, I don't know how much a mouse goes to the local shop, but it gives you some ideas of the different costs and points. And you can actually goes on. I mean, this was just a table I did for a recent paper, and it kind of goes through all these kind of different technologies and what they're good and bad at. So it's a real minefield of technologies and techniques. All of them, but whatever you kind of after, one of them will solve your problem. It's just getting that right combination. So I thought I would quickly just do a quick slide about the kind of applications that we used for electronic noses. So the main application area originally was, food and cosmetics. And the number one, the whole electronic nose field was started by Bass breweries. And they wanted to measure the quality of beer. And they basically funded the initial electronic nose work back in the 1980s and 90s. So this was one of the big things. Rotting fish was number two. I couldn't tell you what third one is, I can't remember anymore. And then you go around things like the obvious areas, which are kind of gas emissions and manufacturing processes. Environmental pollutants and waters, that's kind of what you're interested in. Anybody who works in my kind of field will obviously be involved in homeland security. I probably can't say too much more about that, but you can think. And of course, a large area now in medical research, measuring odors from kind of breath and things. So it's really a diverse area, which it will go to water. Now, I thought whilst I had you all, we kind of talked about some of the challenges. And I think the last speaker mentioned this, that we are attempting to mimic human perception in some way. And there is still a question of, it's very difficult to define what an odor is. I had this conversation with George for many years. The other problem that we have is that sensors don't respond to odors, they respond to gas and volatiles. So what the sensor detects and what's in the air might not be the same. For many things, it'd be fine. So for gas emissions, you have to carbon monoxide, you put a carbon monoxide sensor in there, it's all going to be great. But for complex odors, this is actually quite tricky. Is that array unique? So you've got your sensor response, but if you've got two chemicals that are fairly similar odors, will you be able to separate those out? And you get this kind of issue where, you can have gas molecules and variants in natural environments where you have slight variance in oxygen level or some other gases, which as humans you can't smell, but could distort the output. And this idea of detection limits, etc. I think your last speaker had a really good talk about this. So it's really difficult as an electronic nose person to be able to say, we're definitely measuring an odor. We're basically measuring chemicals, but whether or not they are exactly what the human person is measuring is a whole separate world of pain. And in fact, it gets a little bit worse. So this is just a common group of odor detection thresholds. And so I got a very large table. And basically, green is really easy. So as an electronics engineer, I can do green without any problems. So I can pick these molecules up and detect them with these kind of odor detection threshold, not a problem at all. The blue, I can manage if I really work at it. And if I apply various tricks, I can detect these at human odor detection thresholds. The kind of orangey set, I was going to do these originally red, but I thought, oh, I can't do that. But the red set is the problem set. So these are molecules which have got a very low odor detection threshold and are really crazily difficult to detect using almost any technology. So this is kind of the limitations. If you are, if it was a process plant or if you're looking at gas emissions, the most likely they'll be in the kind of green and the blue section. If you're looking at some specific odor sources like landfill, you might end up in this blue section, in which case it's really tough going. So just something else that's happening kind of within the field. So we are trying to kind of develop standards now for odors and odor analysis that deals with these problems. So the idea of this kind of human perception and these very complex odors. So I work, there's a number of European things, but I basically work with the IEEE in the US, and we're kind of creating standards at the moment for electronic noses to try and answer these questions and to create ways of comparing machines. So the kind of purpose behind this is that we can create series of standards for different things. So water quality is one of them that will happen. And you can have a way of comparing different machines and different instruments for your thing. So this is basically how far we've got. So I'm just doing the baseline stuff. And you are welcome to kind of come join the water quality one, etc. when we get there. So this is, there's already kind of 4 groups, but at the end we'll have 33 standards for odor analysis in different things. And these 4 at the moment are the 4 active ones. So there will be, there is a water quality one. But, you know, so we are trying as a group to kind of develop technologies which are, or develop standards to try and help people in the field who are not experts in electronic odors. So, right, so then when I basically was creating this, they said, give some examples. So I was struggling a bit actually to find some water examples. So this was the only one that I had in my back catalogue. So this is a thing that we did. I don't even can tell you the year we did this in. So we were interested in measuring pollution in rivers and ponds and things. So this was cyanobacteria. And we wanted to look at the odors from cyanobacteria and see if we could tell the difference between toxic strains and non-toxic strains. So this was done in little vials. So these are kind of 500 ml vessels, and then we grew these kind of bacteria in the different kind of vessels and went switch between. So the idea was that we basically started this with a very low bacterial count, and then we tested this for 40 days with analyzing the odors from each one for 50 minutes. So basically this, you can see how all this because of the picture of the computer. So this was our electronic nose, this was our data collection, and then we basically had a load of these vessels filled with bacterial water, and we took the headspace in each one and took the readings. So this is a Fox 2000 nose, so it has 6 metal oxide gas sensors. So this is kind of from the 2000s, and then we took it to the data. So this is the kind of thing you would get. So these are the different gas sensors, and because these are N-type, you get this fall in resistance. So this output voltage you could consider as resistance, and you can see that one is the toxic one, and that's the non-toxic one. And you basically go around. So each one of these, you test each one in process, round and round and round, and we did this for 40 days. And if you do something like a simple principal component analysis, you can separate these groups really good. So electronic nose did a really good job of separating kind of toxic from non-toxic bacteria. The most interesting thing was that we could also separate the growth phase. So we broke the thing into various, lag, growth, stationary, late stationary growth phases. And we could actually tell you what growth phase that bacteria was in by the kind of odors coming off the electronic nose. So each one of these has a distinct odor. And you can go have a look at the paper if you're kind of more interested. There will be more work on this since the time we did this, but I thought it was the only thing I could think of. So another project which I thought I can actually talk about. So these are smelly cars. So this is a project we did with Hyundai. And this was an international project between 4 different universities, and actually 5 different universities in Hyundai. A couple in the UK, a couple in the US, and then this was Hyundai US. And basically, their problem was that cars just smell. There are cars on their production line that just smell. And you might have 100 cars, and one basically almost has to be scrapped because it's so bad as it comes through. And then, so the question was for them, how do we take these on the production line? And we threw at it a whole pile of different sensor technologies. So these are all different commercial electronic noses. And then we used a human panel as our gold standard. So Troy Nagel, who ran this from NC State, basically organized us military-like to try these different odors. And basically, what we discovered was the electronic nose was really good at doing this. But the best way of doing it was actually combining the best of different technologies. So what I kind of wanted to show here is the idea that you can mix and match technologies to get a better result than you would do from a single technology. And you can combine different electronic nose sensors and different ideas together. So basically this was, the best result was here. This is kind of signal to noise ratio. And if you took 5 sensors from a different combination, you got the best performance. There was more work we did after this, which I can't talk about, but we did solve that problem. And they now implement a monitoring system in the US for their Hyundai cars. So this is just basically the different, these are the different universities. So that was the optical systems. This was a polymer. This was metal oxides. This was FET, etc. And it was combining these together to produce the best result. Another thing that's happening quite a lot in the gas sensor field is this idea of miniature noses. So this was something that I could talk about that we did as a bit of fun as a student project a couple of years ago. So the idea was to create a miniature nose system, which is a wearable. So basically this is a watch and you strapped it to your wrist and then you could go for a walk and then it would measure the odors wherever you walked. So this was a little board that we did, and it's got some gas sensors on there and a few other bits and pieces. And then this would link to your phone, and then basically you could download the data as you walked along. And this is just a list of sensors that we added to it. So we stuck an oxidizing sensor on there and some VOCs and temperature humidity. So this is kind of the thing. So this is my wrist with a different shirt on. This was one of the prototype systems. So I used to walk around my local cities where I live and try these out, measuring VOCs. But you could do things like this. You could create odor maps of, as you walk around. Oh, I called it POG because I thought it was quite humorous. So it stands for personalized, I can't remember what it stands for, actually. But as you can see, as we walk around, the kind of stronger thing gives you higher smells, and as you go to nice green areas, it drops. So the reason I kind of showed this is this idea that sensor miniaturization and the formation of these miniature noses is a real hot topic at the moment. And some of the sensor manufacturers are really going for it. This was something we did a few years ago, and we have later versions, which I can't show in the presentation at the moment. But it gives you an opportunity to basically walk around environments and do odor mapping or do safety, etc. So most of the current ones, kind of commercial devices, are for dangerous gas, etc. And this was different because we were trying to do odors and other environmental pollutants. So, but you can see, the kind of thing we can get this little GPS connected and mapped. So, kind of electronic nose has been with us for a long time now, so 40 years. I'd like to say I've not been working in the field for 40 years. And I think that there's really been a lot of advancements in sensor and data processing in the area. It does have some really useful advantages over kind of analytical platforms. It's usually the cost. So they're cheaper, you don't need specialized facilities, you can run them on batteries, they do give you a real-time result. And all of these are really useful. And you're starting to see more of these kind of in industries. I don't know if it's made into the water industry. I do know that there's an electronic nose manufacturer in the UK for water quality, but in kind of other areas, they're becoming quite common. And I think that there's loads of opportunities for this. And maybe that this will be us walking around our factories and water facilities into the future. So finally, before I finish up, I'd like to say that as the president of ISOX, I thought I'd best put a slide in about this. So ISOX is a society which is run as a charity to support those who are interested in electronic noses and artificial olfaction. So we do have a lot of members, and we basically give a load of free resources and expertise out in this area. So I'll put the website on there, and you can kind of, if you've got any questions, you can go have a see what thing, and we kind of provide support. So one of our big things is kind of teaching about artificial olfaction to the field. And we have our conference, which will be next year in Portugal, of course. So I will be there in Portugal in person to give a talk. Hopefully by then, the whole COVID thing will be much easier, and we'll be able to travel much easier. Okay, I think that's it. Thank you very much.
Thank you very much, James, for this exciting talk.
I don't know if it was exciting.
Yes, it was for us. It's a little bit like science fiction sometimes.
Oh, well, I did manage to get a photograph of. Do you know how difficult it was to find that photograph? I could not tell you.
Okay, so are there any questions from the conference room or via chat?
I'm very happy not to tell if there's no questions.
I have one, James. In drinking water, we go for sensitivity, for very low limits of detection. And I saw in one slide this ion mobility. Do you think that this technology has a future for water quality control?
So we did. So I haven't done water quality, but we have done a lot of things in, oils and other kind of liquid phase materials. So I think that the technology, I've got to be careful because I'm trying to think of what I can say. So a good example was we did a lot of work on coffee. So we did a lot of kind of quality standard on coffee, and where the window of a person's acceptable of coffee is very small. And there are various large coffee companies who are very keen to ensure that their products are within a very tight specification. And they're using these technologies for exactly that. So yes, I mean, water would be very easy to do and get very tight, high quality results from.
Thank you, James. There is a question from Inge Elferlich. Thanks for your interesting talk, James, for the cyanobacteria detection of toxic and non-toxic strains. Did you find there was one chemical you could detect that showed the difference, or was it a whole range of chemicals?
So remember that these are electronic noses. So you're not analyzing individual chemical components, you're analyzing the odor as a whole. So if you think about your human olfactory system, if you smell a strawberry, you don't go, oh, I can smell, grassy tones and this tones and that tone. You see it as a hot single smell. So the electronic nose system will not understand that or separate the individual chemicals. It is seeing it as an odor. So you couldn't tell which that chemical is. So what we usually do is that I have a high-end GCMS system. So we will do, big, larger batch of samples through our electronic noses, and we'll take a small batch of samples and run GCMS so we can try and work out what those odor analysis, those kind of chemical components are. There is a whole separate set of issues around that, actually, depending on how your GCMS is set up. But no, so you can't tell what the individual chemicals are without doing some further analysis.
Okay, thanks. Other questions? If not, I have one more.
Oh, so close!
What about biological sensors? I once read 2 or 3 years ago a paper with a sensor for geosmin, which is an odorous compound typical found in water, that was based in cells from a nose of dogs, in receptors. So what about this technology?
So that comes into kind of two camps, actually 3 camps. So the first camp is that you train an animal to detect the odors you want. So a good example is that the US military train bees to detect explosives. And they get a group of bees and they train them to thing, and they flap their wings really hard, and they stick them in a little box, and they keep them for 4 weeks. And then after 4 weeks, because they're basically pinned down, they're not free and easy. And then after that, they send them back, and then they go back to their normal lives. So that's the kind of one end of the biological spectrum. The middle end are, I'd like to say that as an electronics engineer, I'm kind of, but basically they take some rats and they take the top of the nose off of the rat, and then they go in with electrodes, and then they measure the electrical signals from the biological system. I have to say I'm not overly comfortable with that, but there are various countries in the world that this is their big thing, and fair enough. And then the third group is where you're replicating individual olfactory receptors. So you're actually growing olfactory receptors. The downside with this, so they're quite interesting. There's a kind of number of groups working on this. The problem is that they're quite difficult to grow and they don't last very long. So if you think about your own biological nose, you replace all the olfactory receptors every 4 weeks. 4 to 6 weeks, you have a whole brand new nose, if you know what I mean. I don't know if that exactly makes sense. So if you're using an olfactory receptor biological system, you only have that lifespan. So, so it'll be really good for a short period of time. They degrade fairly rapidly, and then you have to make new ones. So that is the kind of downside. Just to, to give you a comparison, I mean, a metal oxide sensor looked after well will last, 5 years, 10 years. And an olfactory receptor you might get 4 weeks out of. It's one of those, if they solve it, it'll be game changing. But the effort of solving it might be too much in the short term.
Oh, thank you, James.
That's all right.
Anyone else? Or
I'm more than happy to have freedom.
Yes, I think you have, but I hope that also in the future, because these technologies are advancing very fast, maybe next year or we will be alive for 2 years, this network, so maybe we'll have the chance to have an update from James.
So next time I shall come in person if you have it, hold it somewhere nice and warm. Particularly around winter time, it's really good to get away from the UK.
Okay, we'll keep this in mind. So thank you, James. Thanks to all for participating. And with this, we close today's sessions. And thank you all.